Design patterns have been making developers' lives easier for years. They are tools for solving problems in a reusable and general way, so that the developers can spend less time figuring out how to overcome the problem and move on to the next one. You might have already learned about some software design patterns before, for example, singleton pattern. Now, after we have worked on several MapReduce programs, we can see that actually the parallel computing programming is very different from traditional programming. We need to consider the MapReducer framework, data locality, and so on. There are also design patterns for big data programming. This big data programming design patterns will help us to save some time and effort. It is regardless of the domain knowledge or development framework. Even though the higher level APIs, they provide a more convenient way to process the parallel computing, and it will transfer the code into the MapReduce programs. However, these MapReduce design patterns are still important for those higher level APIs, such as Pig and Ham. A design pattern is not specific to a domain, but it is a general approach to solve a problem. Using design patterns is all about the design principles to build better software. Even though MapReduce is powerful, but it doesn't provide general solutions to big data. Some problems can be worked in a parallel way, some are not. And some problems, they can be easily done in a wrong way that couldn't take the benefit of parallel computing. And here, the MapReduce design patterns, we will learn which problems are suitable for parallel computing and how can we use it more effectively. So the MapReduce design pattern is a template for solving a common and general data manipulation problem with MapReduce. There are several groups of MapReduce patterns. The summarization patterns are designed for Hadoop to summarize a group of data, and filtering patterns are designed when a subset will be generated from the entire data set. And data organization pattern is designed for restructure the data into another form. Also, the join patterns, they are designed for the joining procedure with multiple data sets. Meta patterns are patterns dealing with patterns, and the input and output patterns. So today we are going to discuss the summarization patterns and the filtering patterns, which are quite commonly used in big data programming. With a large amount of data, and there are new data coming every day, summarization analytics is very important and commonly used in big data analysis. It is about grouping some similar data together and then perform an operation such as calculating a statistics, building an index, or just simply counting. It gives the top-level summarization view of our data. There are 3 patterns in this summarization patterns group: the numerical summarizations, inverted index, and counting the counters. Many datasets are too large to get any real meaning out of it by reading through it manually. For example, if a website logs each time a user logs into the website and did some user behaviors, it will be very difficult to notice any real usage patterns performed by the users by just looking at the log files. So if we group the logins by the hour of the day and perform a count of the number of records in each group, we can plot this count in a histogram, and it's more clear to see when the website is more active. Okay, that is the motivation for the numerical summarization. The design pattern is a general pattern for calculating aggregate statistic values over the data. Actually, it's very simple pattern, but it's very important to use the combiner properly and to understand the calculation you are performing. The intent for the numerical summarization pattern is to group records together by a key field and calculate a numerical aggregate per group to get a top-level view of the larger dataset. And the numerical aggregation can include the minimum, maximum, average, median, standard deviation, those statistics for the group. And the applicability for this design pattern is that the numerical summarization should be used when these 2 conditions are true. One is we are dealing with numerical data, or we are counting. And the second one is the data can be grouped by specific fields. This figure shows the general structure of how a numerical summarization is executed in MapReduce. The mapper outputs keys to group by, and the numerical values to summarize. Here, the use of combiner can reduce the number of intermediate key value pairs to send across the network to the reducers for some numerical summarization functions, like what we did in word count. And actually, it is also useful when we are calculating the max temperature. And then the partitioner. This is a shuffling step. The numerical summarization can benefit from those partitioners to better distribute key value pairs across the reduced tasks. Then the reducer receives a set of numerical values associated with a group by key to perform the function, get the summary from this set of numerical values. And the output value of the job will be a set of part files containing a single record per reducer input group. Each record consists of the key and all aggregate values for this key. there are many uses for the summarization, for the numerical summarization pattern. For example, the word count, getting the minimum, maximum count, mean, median, standard deviation. For all of this high-level statistics of the data set for a key, the numerical summarization is very useful. This figure shows the data flow between the mapper combiner to the reducer. Here, a combiner, it possibly executes over each of the groups from the output groups from a mapper. It determines the minimum and the maximum values in the first two columns and adding up the number of rows. So here, in group 1, for group 1 and group 2, the combiner aggregates this line by output the same user with the minimum values from this group of records and the maximum values from this group of records, and add up the count. So for the user 1, 2, 3, 4, 5, the minimum is 8, the maximum is 21, and the count adds up to 3. And the combiner may not be applied on all of the groups. So if a group is not combined, then it still be accounted for in the reduced phrase. So this is because the combiner works on the local data node. So for this group with user ID 99999, it's possible that the records are located on different data nodes. Then a combiner will not work to combine them. But with some of the groups combined, it already shrinks the map output to a smaller size, so that this smaller size of results will be sent to the reducer as input. The inverted index pattern is commonly used in MapReduce analytics. It is to generate an index from a dataset to allow for faster search or data enrichment. So in the search scenario, if we have a very large dataset, and if every time we want to search for a keyword, we need to go through the entire dataset, then that's very time consuming and not efficient. So the idea of inverted index is that even though it requires the actual processing at the beginning, but it will greatly reduce the amount of time when we want to search a keyword in the entire data set. So right now, the search engines, the commercial search engines, actually they are building indexes to improve the search performance. So every time we input a query into the search engine, it can give us back the results in a very fast way. It's definitely not going through all the web pages in the entire world, right? So it built the inverted index so that the search engine knows all the web pages related to a keyword ahead of time, and then the results just simply displayed to us. Okay, so the inverted index should be used when the quick search responses are required, and the result of the keywords can be pre-processed into a database called inverted index. And what exactly is an inverted index? That is for all the keywords in the data set. We convert them into a way that each key it's represented as the record that has that keyword. Okay, on the next slide we will show how to do this inverted index in detail. This figure shows the general structure of how an inverted index is executed in MapReduce. So this structure has very similar structure as numerical summarization, but actually in details they are totally different. So the mapper outputs the desired field, the keyword for the index, and the unique identifier as the value. Okay, here the unique identifier is for the record. Okay, it's not for the keyword. So for example, if we have a web page as a record, then the unique ID is the ID for this web page, and the keyword is it could be one of the words in this web page, and there could be there are multiple keywords for this web page. Okay, this unique ID is very important here because it's going to be the only reference that used in search. So for a query, we found the unique ID that is related to the query, and then this unique ID represents that record we can link to. Okay, then for combiner, combiner is optional if we are using the identity reducer, because the combiner will create some unnecessary processing, so the combiner is not always useful. Here then the partitioner determines where values with the same key will be copied by a reducer for final output. So it shuffles the records so that the reducer can get the input of the same keys. Then the reducer receive a set of unique record IDs for input for a keyword. Then these IDs will be grouped by some unique delimiter, or they can be written with the input key. So the final output after the reducer is a set of part files that contain a mapping of field values to a set of unique IDs of record containing this associated field value. So for the web page example, this output will be a set of keywords, and for each keywords, it has a list of web page IDs that contains this keyword. Then every time we want to look for a keyword, we just go to that line in this inverted index, and there is this list of web pages are what we are looking for. Okay, counting with counters. The intent is to have an efficient means to retrieve the count summarizations of large data set. This pattern uses the MapReduce framework counters utility to create the global sum on the map side without producing any output. So we have had the counter example previously, and this is the pattern associated with a counter. And the applicability is it should be used when the following two conditions satisfied. One, we want to gather counts of summations of a large data set, and the number of counters we are going to create is small. So that means we only want to have not a large number of counts from the data set. This figure shows the general structure of how the counting with counters pattern works in MapReduce. The mapper processes each input record at a time to increment the counters based on certain criteria. The counter can be incremented by 1 if it's counting a single instance, or incremented by some number if it's executing a summation. That's the logic of the counter. Okay, then these counters are then aggregated by the task tracker running on the task and incrementally reported to the job tracker for the overall aggregation. The counters from any field task are disregarded by the job tracker in the final summation. This job is map only. There is no combiner, no partitioner or reducer required. Filtering patterns is another group of patterns. They deal with the cases that we want to extract a small amount of records from the entire data set. So since we have a very large data set, we do not often do analysis on the entire data set directly. So the filtering process can help us to find a small subset of data based on the criteria given. Then this small subset of data can help us to for example, take a look at the data or have some brief idea about the data. And there are several patterns for in this group, including filtering, Bloom filtering, top 10, and distinct. Filtering is to take a set of subsets that we are interested in and we want to focus on. Then we have, so for filtering, we have some evaluation function that determines whether we would like to keep this record or not. The applicability for filtering is that the only requirement is that the data can be passed into records that can be evaluated in some way to determine whether they are kept or not. So filtering is very widely applicable. This figure shows the structure of the filter pattern. It is quite simple, that it doesn't require any reduce part of MapReduce. For every mapper, it takes in the input speed, and based on the criteria determine whether to keep a record or not, then directly output the selected records. So the mapper is, so the output of the job is a subset of the records that pass the selection criteria, and the format can, so the records including the formats, the content can be kept exactly the same as the input records. For extremely large data set, the filter is usually the very first step that we perform on the data. It has many use cases, including to take a closer view of the data, to track a thread of event, and many more. All of this help us to reduce the size of data in a meaningful and useful way. And the filtering is basically as efficient as the MapReduce can get, because the job is map only. Because no reducers are needed, the data will not be transmitted between the map and the reduce data nodes. And since there are no reducers, there's no sorting phrase, and there's no computation for the reduce phrase as well. So that is also the reason why we will do the filtering as our first step, because it's very efficient. So for example, if we want to get some information, some aggregated information for a group of users out of the entire user, we first filter all the data and then do the aggregation. We can get results. We can also do the aggregation and filter out this group of users, but this will take extremely different time spent on those tasks. So filter first will first decrease the number of records, and then the next step processes will be run very fastly. The Bloom filtering is very similar to the filtering. The difference is that the filter criteria is based on a set of we call the hot values. So if the feature of the record matches one of the values in in the set, in the given set, then it is kept. The applicability is that first the data can be separated into records. This is the same as filtering, and then the feature can be extracted from each record, and it could be matched with a set of hot values, and there is a predetermined set of items for the hot values, so that we can compare the feature of each record with this predefined hot values. This figure shows the structure of Bloom filtering. It has two major components. The first step of this job is to train the Bloom filter from the list of values. So this step is basically loading the data from where it is stored and add each item to the Bloom filter. Then this trained Bloom filter is stored in HDFS as a known location. Then the second step of this pattern is to do the actual filtering. This is similar to filtering. So it just so for every mapper, it just loads the Bloom filter from the distributed cache, and then it iterates from the record and check the Bloom filter to match with the hot values in the Bloom filter. Then each input record can be determined whether it passed the criteria or not. Okay, the next filtering pattern, top 10. It's called top 10. Actually, it's to get the top K records from a data set for a given criteria. For example, for all the students at L'Oreal, we want to get the top 10 students who, maybe top 50. We want to get the top 50 students who run the fastest. So this requires, this pattern requires the data to be able to be compared in some way. Then we can get the top ones, and the number K that we want to extract should be much smaller than the total number of records. Otherwise, we can just do a sorting. Okay, here is a structure for the top 10 pattern. This pattern utilizes both the mapper and the reducer. The mappers will find their local top K, and all of the individual top K sets will compete for the final top K in the reducer. Since the number of records coming out of the reducer is at most K, and the K is relatively small, we will need only one reducer. Okay, sometimes we want to get the distinct values from a data set. For example, for the weather data set, there are multiple stations that report the weather every day. Then out of the entire data set, what are the unique stations? Then we will need to use a distinct pattern here. The intent for distinct pattern is we want to find a unique set of values from some similar records, and the requirement for the pattern is that we have duplicate values in our data set. Okay, for this pattern, in the map phrase, the map function, it gets the record that we want to find the unique set of values. And then for the reduce phrase, the record will be emitted, and there's nothing else is required for the output.